Okay, welcome. So we're going to be starting our weather unit, and what that entails. Just know that school trains us to memorize bits of information and then kind of throw them back up on a test and then forget about them. And this unit's going to ask you to learn those bits of information but not forget about them, but rather than to smash them together and make them into something new. And so we're going to be looking at different variables as we go through this unit, because meteorology is the study of current atmospheric conditions, weather, but it includes lots of different things. We're going to go into the worlds of chemistry, physics. We'll look at a little bit of climatology. We're not going to go so much into the ecology and oceanography because we just don't have enough time. But that's kind of the study that we're going to be in. If you look at meteorology as a science, its goals include understanding, predicting, and artificial control. Artificial control, not so much, because it has a lot of ethical implications. Think to a tornado or a hurricane, and if you could stop that or deflect that, if you deflect it, you might push it into a different community, and is that ethically okay? Or if you actually were able to somehow stop it, it actually takes moisture away from much of the rest of the nation, and is that something you really want to do? So there's lots of different ethical ripples that go with controlling the atmosphere, and it's actually not very effective either. So meteorology, while it dabbles there, it isn't all about there. And so one of the things, of course, then when you start thinking about weather is, the meteorologists, they're never right. If you kind of think about that, how often is your meteorologist source right? Whether it's the internet or the radio or the web, or I already said the web, or your TV or your app on your phone, why aren't they right? One of those things is because of all the different variables that go into meteorology. It can be air pressure, atmosphere, water and water vapor, the different heat sources and energy sources that go in there, the wind and the air currents, and the global rotation and effects of wind. Those are the different variables, the pieces of information that we are going to study, and we'll look at how all of those play together. So those are those first variables that are on your notes there. And then how do those variables interact, and what does that mean? There are four pieces of information, or factors that go into a meteorologist's forecast as we determine whether they're right. First one is observational, like whether you can just go to the window or you're out your door and look out. The second one is actual data collection, so that comes in the form of radar, satellites, weather stations, lots of different areas. The third piece, all of that information, observational and data collection, goes into a computer model. There's many different computer models, anywhere from local to regional to national to global, and there's up to the meteorologist to interpret those and to choose those. So that's a place that some things can go wrong, and time is also a factor in those. The further out in time, the less reliable they get. But the last piece comes down to you and I. Audience interpretation. My favorite example of this, and how we interpret that forecast that the meteorologist gives us, my favorite example of this is a 30% chance of rain. Now you and I take that usually to mean, well, there's a 70% chance that it won't rain and a 30% chance that would rain. But picture it more like a pie chart. So color in the 30% area and leave 70% of that open. What that really means is each meteorologist has a forecast area. So if you put him at the center of the pie graph and the circle represents his forecast area, what he or she knows is that 30% of that viewing area, or that forecast area, will receive precipitation. So, and if we use that 30% example, if you lived in the 70% of the viewing area where it didn't rain, you'd say, that guy was right. And if you lived in the 30% area that the precipitation was going to occur, you'd say, that guy was wrong. It rained hard here today. And so all of a sudden, that audience interpretation becomes a big deal, because that changes your perception of whether that meteorologist is right or wrong. And it's usually the audience interpretation of what the meteorologist says that makes them right or wrong. So that's a huge thing. Hopefully by the end of this unit, you will have a more knowledgeable way to interpret what that meteorologist says, and you'll notice that their accuracy tends to appear a little bit different in your eyes. All right, so I mentioned before we're going to be talking about variables, and we're going to look at each variable individually to help break it into chunks for us, and we're going to break those down. I say a different variable each week, but this first 2 to 3 weeks, we're going to slam you with quite a few of those variables. This week we're going to look at atmosphere, energy, heat, and we're going to start to build on those. As you miss things, I'm going to encourage you to keep track of these YouTube videos. Make sure you're watching those. When we talk about weather information, you and I in our class, we're going to focus on maps. These are generated from individual data collection stations or weather stations. And then that information is compiled into a weather map. And then those go into that's what the information, those observational information that goes into the models. The first one we're going to look about is the atmosphere. And so one thing I do need you to know is what its composition is. It's mostly nitrogen, a little bit of oxygen, a teeny bit of argon, and an eensy bit of everything else. Do you need to know the numbers? No. You just need to know what's the major component of our atmosphere. Every time you breathe in, 3/4 of what you breathe in is nitrogen, something that just goes into your body, goes out of your body, and does nothing for you. The 21% oxygen, that's what we tend to worry about. The things like the trace gases, like carbon dioxide and water, they're going to play a major role in what we're going to be learning about over the next month and a half, but they are actually trace gases, something that makes up a tiny little portion of our atmosphere, but makes a huge big ripple when stuff goes on with both water and carbon dioxide. Dust and pollutants vary with our location, so you think about, if you travel to Los Angeles, they might have a smog warning or something like that where you're not supposed to be outside, or we don't have that here in Omaha. That's because that dust and pollutants varies with location. The other thing you need to know about our atmosphere is its structure. It has layers. Some of you learned some of these in 8th grade or 7th grade. We are only going to ask that you know these 4 main layers: the thermosphere, the mesosphere, the stratosphere, and the troposphere. If you go and that's top to bottom, so we live in the troposphere down at the surface. The thermosphere is the one up at the top. If you want a mnemonic, a memorization device, Too Many Stupid Tests would work with that arrangement there as it appears on the slide. But one trick with mnemonics that I like to tell people is use a naughty mnemonic. Make it so naughty you can't tell me as your teacher, I don't want to hear it, la 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 la, because it'll make you laugh. So think about something naughty that would fit those words. And now as you're giggling, I know that you'll remember it, because as you giggle over that triggers those happy brain hormones that we want to get going to help learning more easy for you. So hopefully a naughty mnemonic there would work. Each layer is separated by a pause layer. So a tropopause happens here between the stratosphere and the troposphere. The stratopause happens here, and it literally is like a fence or a gate. These layers have distinct levels. They change over time, so they're not always in the same spot, but we can find them based on the data. And then the mesopause is here between the thermosphere and the mesosphere. So it's almost like you'd go up, you'd have to pause and go, oh, here's the stratosphere, and then you'd be in the stratosphere, and then you'd pause, and you'd go into the mesosphere. So at the stratopause is that boundary between those 2 layers. Space, or the other layers you might have learned in 8th grade, are the exosphere and the ionosphere. You don't need to know those. Those are more, as far as I'm concerned, fun to know than need to know. So we do want you to know these 4 layers. Here's a book image. It's actually on page 480 of our textbook. I know you all are so familiar with that. But this is a very common one. We'll talk about what this red line means. Main thing to notice here is look at how tiny this layer is and look at how big these layers are. And this is kind of the image we're going to refer back to as we go. So the first layer is this bottom layer down here, the troposphere. That's the layer we live in. The red line represents temperature. So what you notice is it decreases with height. We're going to talk about the Earth as a heat source. So air is warmer, closer to the ground. And if you think about going up in the mountains, it gets colder, snow peaks, whatnot. Air pressure decreases with height. Here you can think about airplanes. You are in a pressurized cabin. Should the cabin lose pressure, the air masks come down, that sort of thing. And so the air pressure gets lower as you go down. It is the layer we live in, and the top boundary, the tropopause, that is one that you do need to know. You don't have to know any of the other pauses that are listed here. You just need to know the tropopause because that boundary acts like a lid to our weather. It literally keeps the weather in. And if we go back a slide, you'll notice that you can see how this cloud goes up and then it kind of stops right there. That's because the tropopause is acting like a lid. And so that tropopause word, we do need to know that that is the lid of the weather. The next layer up is the stratosphere. And so that one, the pressure still decreases with height. It gets lower and lower in pressure as you go up and up and up through this layer. This is where we find the ozone. And the ozone is interesting because that actually causes the temperature in this layer to increase. The ozone captures UV rays as they enter our atmosphere, and so that increases the temperature here in the stratosphere. Some commercial airplanes will fly here at the bottom. The airplanes prefer the troposphere because that is where it's a little bit easier for them to fly using less fuel. But the stratosphere, they can get up in the stratosphere as necessary to get above storms and such. So supersonic airplanes, those that can cause a sonic boom, would fly here for sure. The top boundary is the stratopause, but you don't need that. The mesosphere is the next layer up. Again, pressure decreases with height. Hopefully you can start to sense a pattern. As we go up through all these layers, the pressure is going to decrease. Kind of a fun fact, pressure is so low that if you were to get out of your pressurized cabin in the mesosphere, your blood would literally boil at normal body temperatures. So blood boiling is kind of an interesting, people talk about that when they're angry. We could make it happen. Temperature here decreases with height. Our original pattern is that Earth is a heat source, so just like stepping away from a fire, as you move away from the heat source, your temperature is going to go down. We talked about how ozone makes that go back the other direction when you go up in the stratosphere. The mesosphere doesn't have any ozone, so we go back to that original pattern. As I move away from the surface, my temperature is going to go down. So that's why this line here goes back this direction. So that temperature goes down as we increase our height because there's no ozone there. This is where shooting stars would occur. You finally have enough atmosphere, enough air pressure present for those molecules to bump into a meteorite and set them on fire. And then the top boundary here is the mesosphere, or mesopause, sorry. And then the last one is the thermosphere. Here the temperature increases with height. This one's a little counterintuitive because if I dropped you, don't get me wrong, if I dropped you out in the thermosphere, you'd freeze to death, okay? But the temperature does increase with height, and here's why. Temperature is a measure of how many molecules bump into a surface. And so in the thermosphere, there's so few molecules present that if energy is absorbed by any of those molecules, they start moving really fast. So imagine a person running through the halls during a class period. So it's not during passing period, it's during class period, during the mod, and a person could run from one end of the building, all like starting at our classroom in 305, all the way down to the gym area or down to the swimming pool, and it wouldn't take you very long because there's not very many molecules or people present. You could run through there and not have any problems. But if I told you to do that during a passing period, it would take you probably a lot longer to get there because there'd be people in the hallways, lollygaggers, the landing would be full, that sort of thing. It's the same thing here in the troposphere versus the thermosphere. Down here, this is like the passing period. You can add energy to a molecule, but it can't move very fast because there's too many molecules present. Here, this is like running in the hall during a class mod. If I give that person energy and say run, they can, and they can do so very quickly because there's so few molecules present. Many of you asked about the radiometer, the black and white glass ball that's in the classroom. That's much like the thermosphere. I'll explain that in a different YouTube video, and I'll make sure that you guys have that as well. This is where, also in the thermosphere, where we see the aurora borealis. So this is where the northern lights occurs in that thermosphere. Okay, so for each layer, you just need to know the temperature and the air pressure and then some of those objects and be able to identify those from a list. So those would all be multiple choice type questions on the exam. The next variable we're going to add today is heat energy. Heat is different than temperature. I talked about temperature, remember, as a measure of how many molecules are bumping into a surface. Heat is actually a measure of how much they're moving. The faster they move, the more heat energy we have. The slower they move, the less heat energy you have. That's going to be a huge part of this unit, so we're going to repeat that over and over. You also need to know the three main forms of heat energy in our atmosphere. They're conduction, convection, and radiation. So hopefully you remember these from 7th, 8th, 9th grade, but conduction is when molecules crash together to transfer heat energy. Convection is by mixing or circulating, and radiation is by electromagnetic waves. So I don't have to touch something to know how hot it is. And the thing we have to keep in mind for our atmosphere is heat flows always from areas of high temperature to areas of low temperature. So when you put your cold fingers on a hot mug of cocoa, the heat energy is leaving the cocoa in the cup and going into your fingers. That's why it feels warm. However, when you hold an ice cube, it feels cold because the energy is leaving your hand going into the ice cube, and so it feels cold to you. So heat flow is always from high to low temperature. So if we look at that conduction, conduction is by molecules touching. So here you see, in the image, you see a metal, call it stick. And as we hold it over that candle flame, these molecules start moving fast. Well, they kind of give a hip check to the molecules next to them, and that gets them moving. So I always have a picture of friends on a dance floor, and you've got the one curmudgeon who won't dance, and so then the peppy person of the group kind of hip checks the other kid that won't dance, and what you see is finally they're like, okay, fine, I'll dance, and they start dancing. So it kind of moves down the line of friends that way. Same thing here, conduction, when one molecule bumps into another, that is what then makes the next molecule move. Air then becomes a very poor conductor because the molecules don't touch. You can feel this as you move your hand through the air. You can feel the wind, you can feel those air molecules as they bump against your skin, but you're able to move through it very easily because they're so far apart. So conduction is not such a big deal when we're talking about meteorology. Convection is going to be a big deal. We're going to talk a lot about convection. And this is the idea that hot stuff rises and cold stuff sinks. So if you've ever had hot coffee and you poured cold milk into it, you watch the milk sink down to the bottom and then start to swirl through your coffee to mix up. That's convection. So you're adding the hot coffee, you're mixing it with the cold milk, and as the two fluids mix, now you have a little bit warmer milk and a little bit cooler coffee, and you have this nice drinkable drink. And so wherever molecules are free to move, that's where you'll see convection. So this happens in water, this happens in air, anytime you have a fluid like a liquid or a gas. The main thing that's hopefully you remember is hot stuff rises and cold stuff sinks. So whenever you hear your instructor say hot stuff, you're going to answer rises, and whenever we say cold stuff, you're going to say sinks. So if I say hot stuff, you say, if I say cold stuff, you say, so one more time, hot stuff rises, cold stuff sinks. Very good. And so that's convection. The third form of heat energy transfer is radiation. This happens by electromagnetic waves. In our spectroscopy unit for measuring the universe, we looked at visible light. Electromagnetic light waves are just another wavelength on that spectrum, just outside the range we can see. What's important about radiation is it doesn't need molecules. So our conduction needed molecules to touch, and convection needed molecules to mix. Radiation doesn't need molecules, which is important because that means it can travel through outer space. there's not enough molecules between us and the sun to get energy here in any other way. So if we didn't have radiation, there would not be life on Earth. What's really cool about radiation, though, is all objects, whether it is your freezing cold toes, your warm laptop computer, the pencil in your hand, whatever, all objects emit radiant energy. If you're hotter, you emit more. If you're cooler, you emit less. And so this is the whole concept between night vision goggles or night vision cameras and how they work. They are looking for that radiation coming off of any objects. And so the other thing is objects that are good absorbers are also good emitters. So if there's something that can absorb a lot of heat energy, think like a black sweatshirt, a black piece of paper, it can also emit a lot of energy. So if it's a good absorber, it's also a good emitter. It can give it back off. Now, why is that important? Well, Earth gets all of its incoming energy. Every last piece of energy here on Earth at one point or another came by the sun. Whether this is fossil fuels, that is from the sun first, then it grew a plant, which got eaten by an ancient animal, which then died, and then formed into coal, natural gas, oil. Or whether it's from something like the food you eat. Again, energy from the sun grew a plant, which then either fed a cow or you ate a bean or whatever. So all of the incoming energy comes by radiation from the sun. 30% of that radiation bounces before it ever does anything from the Earth. So you don't have to know these 25%, 5% things. Just know that 30% bit. 30% of that energy gets bounced off the atmosphere or the clouds or the surface of a glacier or the surface of water somewhere, whatever. It bounces. 20% gets directly absorbed by the atmosphere and clouds. But 50% of incoming solar radiation is absorbed by land or water masses on the surface. So most of the incoming radiation hits the surface and is absorbed there, not by our atmosphere, but at the surface. That is huge because good absorbers are good emitters. So the atmosphere if we compare, by comparison, is not a good absorber, so it's not a good emitter. The surface is a great absorber and a great emitter. So the three numbers that you do need to know are that 30% here that bounces before it ever does anything from the Earth, and that can bounce by the atmosphere, it can bounce from the clouds, or it can bounce from the land or the sea. You don't have to know that this 5, 20, and 5. You just need to know this 30 from reflection. 20% actually gets absorbed here by the atmosphere and clouds, but this is the number we really need to remember. 50% is absorbed at the surface, by land, by the ocean, by whatever. 50%. Huge. That's huge. Okay, so if you don't think that's important, that's huge. Why? Because the atmosphere gains energy from the sun, from above, but it also, good absorbers are good emitters. So the Earth, as it absorbs that radiation, also re-emits that radiation. And so what happens is that sunlight as it comes in doesn't get absorbed by the sun, but it does hit the Earth. Well, when it hits the Earth, it's re-radiated at a different wavelength. And so water and carbon dioxide in the atmosphere are not excited by that incoming solar radiation, but they are perfect absorbers for that rescattered, re-wavelength energy that's coming off the surface of the Earth. So greenhouse gases like water and carbon dioxide, those ones I said that don't make up a very big part of our atmosphere, are really important now, because what happens is those gases now can absorb that re-radiated energy, and then that is what then will heat the atmosphere even more, is that re-radiated energy. So the atmosphere is kind of heated like a sandwich. Okay, it's heated from above by the sun and from below by the Earth. And so the atmosphere is that hamburger in the middle. The heat sources are the buns. And if I were to draw this picture correctly, I would flip that over. I would put this bun on the bottom and this bun on the top, because our largest heat source is the Earth, not the sun. That's kind of mind-blowing to me. Like, I would have never have thought of that on my own. I would have never said, oh yeah, the biggest heat source is the Earth. What? No, it's the sun. Wait, what? Brain freaking out. So that atmosphere being heated by the Earth is the biggest heater is like craziness. So here's what I was talking about before with that new wavelength. So when the sun heats the Earth, it's all these beautiful, small, tiny wavelengths, and they all come in these nice parallel lines. But when it re-radiates that energy, notice how it's coming off at a longer wavelength. Those wavelengths aren't quite as tiny as these. They're nice and stretched out. And notice how they come off in all directions. And so water and carbon dioxide, this is why they will absorb those so readily, because they're at a different wavelength and they're all scattery. So the other piece we have to keep in mind is the Earth isn't heated evenly. It's not a rotisserie chicken. There's several things that go into this as well. And this is a good place to stop in your notes before you continue any farther. You should have the first couple of pages. You should now be on that back page that's got a great big table on it, and it talks about the different ways Earth is heated unevenly. So I'll give you a second to pause, go back if you need to. All right, so now we're going to talk about the Earth is heated unevenly. First off, land and water both heat differently. Water doesn't heat very easily. It's got what's called this chemical property called a high specific heat, which means it takes a lot of energy to raise or lower water's temperature. You've run into this if you've ever had to boil a big pot of water to make spaghetti or mac and cheese or something. You put the water on the stove and you wait and you wait and you wait. And you're like, did I turn the burner on? Yeah, I did. Why isn't this water boiling? It takes a long time to boil that water because water can absorb a lot of heat energy and it can release a lot of heat energy without changing its temperature. It just doesn't do it very easily. And so water acts like a heat energy sponge. It soaks up and releases that heat energy without changing its temperature. We're going to talk about that temperature and that heat energy later. It's called latent heat. Latent means hidden. If you've taken forensics, you know that a latent print is a hidden fingerprint. So that term latent means hidden. What this also means is that water doesn't heat or cool as fast as land, and water won't reach the temperature extremes that land does. So any land that's close to a large body of water, like the ocean, has a more moderate climate. So if you think about California, they're a meteorologist. If you've ever been to California, visited there, today it's going to be sunny and 70. Tomorrow it's going to be sunny and 70. The day after tomorrow, sunny and 70. Yesterday was sunny and 70. It's always the same. But here in Nebraska, it's like, hey, look, we went from a snow day on Monday to a cold day on Wednesday to 50 degrees on Saturday. That was literally our week, and that is normal because land heats and cools really fast. The other thing with our Earth being heated unevenly is elevation. Higher elevations, if I go up in a mountain, it's cooler. We already knew that from our atmosphere structure. But also your global location makes a difference. Your latitude, how far north or south. If I asked you where to send me if I was too cold, you'd say go to the equator. And if I was a hot person, go to the poles. You'd send me to the poles. Those latitudes make a difference. So Earth is for sure not a rotisserie chicken. Here's a picture of that temperature distribution if we're looking at latitude. You can also watch how it changes over how that impacts the course of our years. This data was from 1959 to 1997, but the current map would look a lot different, but still kind of have that same pattern of hotter in the middle, cooler at the poles. The difference is nowadays this red band is wider and goes up higher in the north, and some of our purples actually have disappeared. So I'll need to update that picture. The uneven heating then has effects, and those are the effects that we're going to be studying. Each of the variables that we give you each week is going to ripple outward, and remember how we're going to talk about chasing your variables. You've got to see, okay, if I know what happens with heat energy, what's that going to do to something else, and what's that going to do to something else? Heat is going to have a direct impact on air pressure, and we're going to look at those as you add variables. So the next variable that we're going to focus on a lot is going to be air pressure.